Okay, so let's consider another static system where we have two objects that are hanging. So let's say we have a little ring, a little metal ring, say, of mass mr, and strings are attached to it such that we have a string here and a string there, and not a great drawing, but there's an angle here, let's say known, and let's say it's the same angle here. So these two strings are holding this object up, and we attach another string to this object here, which connects to another object of some mass B for block or something like that. Okay, so the system is at rest. There are two objects there, and we want to know, let's say, the tensions in the strings. So we can call this tension here T1, this tension in this string here T2, and the tension in this one T3. We want to know what T1, T2, and T3 are. The first thing to notice is that our physical principle is Newton's second law, most likely. That's going to be useful to us because these tensions are forces, so they will likely appear in here, and this should provide a constraint. So the next thing to notice is that there are two objects, and so ma equals F applies to each object separately. And so we could do a free body diagram, isolate the ring, and figure out the forces acting on the ring in the vertical direction and in the horizontal direction. So maybe I'll just sort of describe that. So, imagine the ring by itself, and we want to draw arrows representing the forces. We would have two arrows upwards, right? Because we care about finding the forces in a vertical and horizontal system. But these two forces, T1 and T2, are at an angle, so we would have to find their vertical components. Both of these have a vertical component, which is upward, so they would come in with one side, and then there's a string here attached here, which is downwards. That would come in with an opposite sign. Of course, there's also the invisible gravitational force. So if we did the free body diagram, and then we looked at the vertical component of ma equals F, what would that look like? Well, first of all, the left-hand side, the acceleration side, what's the acceleration of this object in the vertical direction? It's 0. The object is stationary. And so we need the vertical part of this, right? So here's a right triangle, and the vertical part is the opposite side. So it's not surprising that we would have a T2 sine of theta naught. Then we add to that the vertical component of T1, which also involves sine theta naught, right? Here's the right triangle. And so this side here is the vertical component of this. So it's T1 sine theta naught. They both come in with a plus sign because they're both upwards. Then we have T3 acting on this, but downwards. We come in with a minus sign there. And then, of course, we have the weight of the object, the force of gravity, in other words, pulling it down, mRg. And we're done with the vertical components. So we look at the horizontal component because there's still a somewhat interesting horizontal component there, right? We have part of T2 that's pulling the object this way and part of T1 that's pulling the object this way. So there's no acceleration in this direction either. So we have a 0 horizontal acceleration, right? So we're looking at the horizontal component of ma equals F. The left-hand side there is 0. The right-hand side involves the component of the two tensions. Once we've identified that these involve the sine, then these must involve the cosine. So we have T2 cosine theta naught. But now we have to be careful that the T1 cosine of theta naught is opposite. Otherwise, the equation wouldn't make sense. So this immediately tells us that these two tensions are equal. We'll get to that in a second. So we're done with applying ma equals F to the ring. And now we have the other object, the block. So the block, there's only an interesting vertical component, right? There's 0 acceleration in the vertical direction for the block, and that's due So if we made a free body diagram, we would just have T3 upwards and the gravitational force downward. And so that would allow us to immediately write the forces with opposite sign like that. Okay, so we're done. Those are our equations. We've applied ma equals f to both objects. One has two components, the other one has one. Well, the other components, of course, are uninteresting. They just say 0 equals 0. So everything follows from this. At this point, it's just algebra. So T3 follows directly from that. If we know the mass, we know the gravitational acceleration, we get the tension T3. So now let's find T1 and T2. Well, this equation here tells us that T1 is equal to T2. Right, when we isolate T1 or T2, we bring this term to the other side, say, and then we solve for T2 or T1, we get that they're equal to each other. So we just need to find T1 or T2 from this equation. And that, of course, tells us that 0 equals 2. Let's say T1 sine theta naught, right? So I'm just going to replace T2 with T1 and get twice this term. I have minus T3 here, but I know what T3 is, so I'm going to replace it with that. And then I have that minus mRg. And so from this, I get T1 and, of course, T2, which are both the same, but they will give me, I'm going to bring all this to that side and then divide by 2 sine theta naught. So I get mb plus mr, the sum of the masses times g, divided by 2 sine of theta naught.